and very last session for our Intro to Machine Learning series. And yeah, we hope that you can learn a lot from today's session, and remember to jot down notes and papers. I have a note to take down the notes if necessary. And yeah, let's get started. So my name is Yong Siu, and today we have two presenters, me and Yo Ziqing. Ziqing, do you want to say hi?
Yeah, hi everyone. My name is Zikin and I'm a year 2 AI student. Yeah, Yongsu, can you stop the background music?
Oh, okay. Uh, yeah. So okay. So yeah. My name is Yongxi, and I'm a year 1 AI student. So today, so if you have attended the session from session 1, 2, and 3, then I guess you will have learned a lot on the fundamentals. But if no, don't worry, we will cover a lot of the basics that you need. So this session does not have any prerequisites, okay? And so now let's start with the teaser, right? What are we going to learn today in the next 15 minutes? 2 hours and 15 minutes. So first, we will introduce what to you all the concept of tensor, okay? And then after that, we'll talk a little bit about pre-processing and loading data into tensor. And then we'll build a neural network with Keras sequential and functional API. And then after that, we'll be working on uh, a small regression example, right? And then we'll build a multi-class classification model. And at the very end, we'll talk a bit about transfer learning with efficient net B0. And so let's start, right? Before we start with tensor, we will first go with some revision. So in artificial intelligence, which I guess you all can see my cursor, right? Can you see my
Yeah,
cursor? Okay, great. Um, so in AI in general, you have machine learning, right? And in machine learning, you are playing with data that are structured in a table form. However, in real world, things are more complicated, right? Things are unstructured. For example, languages, pictures, images, videos. These are unstructured data, and it represents a huge portion of our daily life. And there is a need for such a technique to work with unstructured data, which is where deep learning comes in. Okay, so this is a Venn diagram that allows you to understand the general picture here. Okay, now let's go to the next slide. So what is the difference exactly between machine learning and deep learning? So in machine learning, you have techniques like random forest, SVM, which stands for support vector machines, right? And these were techniques that were really what makes up machine learning and was invented a couple of decades ago, right? For example, if not mistaken, support vector machine was first proposed in the 70s, and these were really pioneers model at the time. Um, and after that, a couple of decades ago, here we are with much more computation power. We are able to do much more complex things, which you can see here in the deep learning column. We can do things like neural network, fully connected neural network, convolution neural network, which is CNN, better known as, which are really computationally intensive, right? And before that, there were some works on this sort of techniques. However, I guess it sort of died down in the early 2000s, where researchers just found out that we have all these fancy techniques. However, there really just isn't enough computational power to do all the computation, right? And nowadays with things like GPUs and a lot of research done on NVIDIA and Google, these techniques become more and more viable. So now let's break down a neural network, right? Um, so in a neural network, you have all these circles here, which are called nodes. Okay, nodes, N-O-D-E-S, nodes. And all the nodes, just like you can imagine the nodes as the neurons in our brain, right? Neurons, they are strongly connected. Just like here, all the nodes, they are connected through this line that you can see here, you know. And this line, more technically, it's called as weights. Okay, for example, neurons, they are connected through synapses and all those things, and it's kind of the same design here, right? And so now to go in a bit more detail, so the neural network flow from left to right, okay, from left to right. So you can see here you have input layers, right? In this case, you have two input layers. You can have more than two, three or four or more. So it will be, one column at the leftmost column is the input layer, right? For example, like I can say that, my input is like, for example, this node represents the number of, like, for example, if I want to do some sort of, like, a natural language work, then it maybe like one word is one node. If I want to do some sort of regression, then the input will be like, like let's say I want to predict the house prices, and my input takes into account like the number of bedrooms, then one node will probably represent the number of beds in one room, and then the second node will be number of bathroom, right? So these are input layers. And then you have the hidden layer. So hidden layer is really what makes neural network really powerful, because it allows you to have a much more complex modeling in terms of the world, because the world is very complex, and you can, when you have more layers, when you have more hidden layers, and it will allow you to do all sort of complex modeling, right? And at the end, you want to have an output layer. So the output layer will be, it depends on your design. So in this case, you only have one output node, right? Sometimes it can have more. And so I think this slide is really good because it shows the design and the code as well. So let's walk through the code. So this is a TensorFlow specific way of writing. So TF stands for TensorFlow, right? And you basically, tf.keras.sequential is the library that you're calling. So when you call the library, you are essentially trying to, write out this design that we have here in code. So first line is tf.keras.layers.input, so that the computer knows that, oh, this is the input nodes, and unit is 2 because you have 2 nodes. It's very simple to understand, right? That's why TensorFlow is very powerful, because with just a few lines of code, you can, do a lot of things, right? And then your dense layer is basically the hidden layer. And then at the end, your output layer is also called a dense layer with a unit of 1. So this is a, general overview on what you need to know on neural network, okay? Input layer, hidden layer, output layer. Hidden layer, you can have more than one columns or layers, and you can have more than 3 nodes, right? For example, 4, 5, 6, or even more. Okay, now let's go to the, so we talk about nodes, right? What about those lines? Those lines, like I said just now, they are weights, and you can also have biases. So you can think of biases, weights and biases. Biases is like, in mathematics, you have y equals to mx plus c, and c is the bias, right? You want to shift the value instead of multiplying it. So that's why you have the bias. And if one thing that you can see here is that all the weights and biases are represented in the matrix form, right? You see here, this is a high dimensional matrix. And the thing that I want to say out ahead is that if you are really interested in machine learning, which I assume you are because you are here, right? you have to be prepared to work with a lot of matrices, and not to be afraid of very high dimensional abstract matrices that you need to picture it in your mind. Okay, so the reason why it's designed like that is because it is very efficient. Because when you do matrix multiplication, you can multiply a lot of you can multiply the first layer with the second layer using matrix multiplication, and that's why the weights are all represented in a matrix form. Okay, so for example, the input is like it can be numbers that represents the color of a pixel, right? And then yeah, I guess yeah, I should have mentioned that the reason why we have weights in machine learning is because not all input are equally important, right? For example, if I tell you that I want to predict the house price, maybe some of the features like the number of bedroom is very important compared to the color of the house. So when you have this sort of weights and biases, you can tune the weights so that it pays much more weightage to the information on the number of bedroom. It's this kind of concept, right? And which I want you to understand. Okay, now let's look at the third slide here that we have. And so what is tensor? We have talked so much about matrices and neural networks, and I said at the teaser I want to tell you what's a matrix. So a matrix is essentially a multi-dimensional array with a uniform D type. And D type is the data type, right? These are all integers in this case. And then these are floating point values or doubles. And tensor, so okay, now I need to go to the collab. And so, and we will talk a bit more from there, right? So introduction to tensor and TensorFlow. What is a tensor? Like I said just now, it's a multi-dimensional array. And then if you are familiar with NumPy, TensorFlow is kind of like NumPy, okay? And then all tensors are immutable, just like Python numbers and string. You can never update the content of a tensor, but only create a new one. So that's very interesting, right? Okay, let's see, we have a chat. Okay, it's a link to the Colab. Okay, if you want to do it together interactively, you can open the Colab yourself as well. Okay, now let's look at first, if you want to do TensorFlow, you have to import the library. So import TensorFlow as TF. It's a standard convention. And then we want to print the TensorFlow version. It's very important to know what version of TensorFlow you're running, okay? Because, or else you might run into all sort of problems later on. Okay, and so we are now running on TensorFlow 2.7.0. Okay. Now, first, we want to show you this picture, which really explains about tensors. When you only have one value, a scalar value, just like a number, say 27, or a number, say 8, it is a scalar value. It's a rank 0 tensor. And from there, you can have vectors. Vectors are just like arrays. However, they are like, instead of writing it horizontally, vectors are written vertically, right? So that's a rank 1 tensor. And from there, you have matrices, which are rank 2. And tensor is just the next dimension of matrices. And then you can have rank 4 tensors, okay, just like in this picture. So this is a 3 by 3, and then you have multiple 3 by 3s, and you can have more and more. That's why machine learning is a lot about high dimensional tensors. And then, okay, so here we have a single number, a number with direction, right? Two-dimensional array, which is a matrix, and n-dimensional, where n can be any number. So let's try an example, shall we? Okay, so we want to first create a tensor. Scalar, which is very, which is understood, right? Scalar value. So how do you create a scalar value in using TensorFlow? You use tf.constant and you put the number that you want. So that when you run it, your scalar, this variable scalar, equals to 1, 2, 3, and the type is a TensorFlow tensor. That is very important because when you do machine learning and you have a variable that is a NumPy array, it's not the same. However, it's not the same as a TensorFlow array. Okay, although they are similar, but you can't do machine learning with NumPy arrays. Okay, so that's why. And there are ways to convert, which we'll show you in a short while. So now we want to check the number of dimension. Okay, so scalar dot n dimension, it tells you it's a rank 0 tensor, like we said just now. And the shape, so you understand more when we show you more complicated example. So now we have a vector, right? It's still the same, okay? TensorFlow dot constant. Why is it constant? It's because it's immutable, just like we have said just now, okay? Immutable, that's why it's TensorFlow tf.constant. And then when we create, so we have created, right? It tells you the type. Okay, now let's check the dimension. Okay, now just now is 1, just now is 0, now is 1. And then it tells you that it's a shape of 3, means it got 3 elements in the vector. Okay, likewise, matrix is a tensor, TensorFlow tensor, shape 2 by 2, right? As you can see here, integer, it's an integer, and it's a in NumPy form. This is how it's like. Okay? And the same thing, we check for the dimension so that to make sure to confirm our understanding, right? It's a 2, just as we have predicted. Okay. How about a tensor, more than 2 dimension? Okay, and then we run. So you can see here, one thing I want to point out is that you use this square bracket to represent. So if you have 1 square bracket, it is a vector. When you have 2 square bracket, like square bracket after square bracket, then it's a matrix, and it goes like, see here there are 3. So this is like a vector, and then in that vector got like a matrix with 2 vectors, and then there's a tensor with 3 matrices, right? Something like that, which is very important. And then let's check our understanding. It should be 3 and 3, 2, 3. Like I said just now, right? 3, 2, 3. Okay. And then creating a changeable tensor. So there's a need to create a changeable tensor. Sometimes you don't want it to be just constant. So this is how you do it. Changeable tensor, instead of constant, is a variable. And you can see here, right, the type is different. Okay? Okay. Now we want to go to operations of a single tensor. So in TensorFlow, there are many things you can do. You can find the minimum, or you can find the maximum, you can find the mean, or you can use the standard deviation as well. Okay, so this is how you use it. Okay, the notebook is available for you to refer after this and play around with it. Now let's talk about one-hot encoding. One-hot encoding, what is it? So, so let's say we have a list, right? And the list got some numbers. What we want to do in one-hot encoding is like, we want to change so that instead of having a list that is made out of decimals, we want to make it more simple so that, because our machine learning is use very simple data representation. So one-hot encoding is basically a way of encoding your numbers. So in this case, if it is 0, instead of writing 0, you put 1 at the 0th element, at the 0th position. And then 1 is 1, because this is 0, 1, 2, 3, so 1. And then this is a 2-second position, and this is the 3rd position. So this is what you call as one-hot encoding, right? Okay, now we have a strong understanding of what is a tensor. And now I want to show you a bit more. So just now we stop here. So this is a tensor. And now let's say we have example here. Our example is that we have an image, right? An image with French fries and pizza and chickens and soda. And first, we want to, in machine learning, it's all about tensor. So we have to turn our image into a tensor. So how do we turn an image into a tensor? An image is basically made out of many, many pixels. And the pixels have color, right? RGB colors. And the RGB colors, they are all numbers from scale to from 0 to 255. So you can turn this image into a tensor that has a high dimension. So as you can see here. And then you fit put it into your machine neural network, and then you fit it, which we'll explain in a short while. And then what I want you to pay attention here is the output. So the output is basically, some numbers, and all these numbers have some meaning. So in this case, it says that this image contains French fries with 83% confidence. So what it probably tells me if I'm reading this slide is that this first number in the output represents the probability of the picture being a French fry. And maybe the second class is, oh, it's a pizza. And the third class, maybe it's a chicken. So now you take the highest value as the, which as the result, right? So if your machine learning model performs well, then it is very accurate. The highest one is the correct one, okay? Now, another thing that I want to maybe tell you is that normalization. Normalization is very important in machine learning because because of how machine learning is designed. Okay, like this is an introduction course, and we don't want to go too much into the detail. It's just a 2 hour sharing session. So normalization is the idea where initially I say that our values range from 0 to 255, and our machine learning model probably won't learn that well. So we want to normalize it from 0 to 1. So we divide all the numbers by 255 so that all the numbers will be in the range from 0 to 1, so that it will be easier to train. That's the idea, right? Okay. Now let's look at the typical workflow for creating a neural network. A typical workflow includes preparing the data, turning it into a tensor, right? And then you want to define the layers and units, which we have here. And then actually, I want to go a bit more detail, right? Preparing the data, turn it into a tensor, just like what I've shown you just now. You have an image of a French fry, and the image to you it's a picture. However, you want to turn it into a tensor, so RGB values. So like this picture here that you see, it's a 2D picture, and it has pixels in the X dimension and in the X dimension and in the Y dimension, right? And all these pixels are RGB colors, and each R and G and B has a value. So if let's say, by the way, RGB stands for red, green, and blue. So let's say the value of red is very high, and the value of green and blue is low. So that means that pixel is very red. The color is very red. So you represent it in that form, and then and basically, like, so let's say your picture is a 2D picture, right? So you want to basically like for example, your pixel is like, you can imagine like dots, and then dot, and then dot. So you have your first column, no, sorry, first row, right? And then your second row, what you should do is that you should, to make it into a tensor, your first row should be followed by the second row, like, so you have a square bracket here, and then the second row is another square bracket. So this is how you make it into a high dimensional tensor, right? A square bracket with the first row of values, and then comma followed by a second row, and then you basically uh, I can't remember what's the correct word, but you basically turn this 2D picture into a like 1D. But however, it's many it's like it's it's how you're seeing here, right? You know, like this square bracket here. So this first row is the pixel value of the first row, and then you comma followed by the pixel value of the second row, and so on and so forth. And then all this is in one another square bracket, right? So in this case, you have a 2D matrix because the picture is 2D, right? It's a matrix form. So I guess this one does not include the RGB thing because RGB has three more like dimensions, so you have to add that. Which, yeah, so that's a bit about preparing the data, how to exactly turn it into a tensor, right? So now let's look at the second one. In the second one, you have the you want to define the layers and unit. Like I said just now, at the very beginning, you have the layers, right? How do you know how many hidden layers you should put? How do you know how many input layers you should put? How do you design your architecture so that it is the most optimum? So you need to know how to define the layers and units, okay? And then the third one is compiling the model, okay? If you learn, computer science, compilation is that you have a very high level code, right? For example, that you see here, like here, in just a few lines, you are able to, right, our member here, Jaheng, shared a picture which really helps us, which can really help us to understand what is like visualizing. If you look at the chat, you can see, right? So you have the channels, RGB channels, and rows and columns, and so this is how you turn an image into a tensor, essentially. Someone raised their hand. Do you have any question? Lim Xing Yao?
So sorry, you may proceed. I accidentally clicked it.
Yeah, it's okay, definitely. If you guys have any question, feel free to stop me. I love to, answer your question and, to help all of you all. And then the third one that we have is we want to compile the model, right? And so you learn in, computer science, you want to compile a model and turn it into like from a very high level code that you have written, you want to turn it into low level machine understandable code. And it's the same situation in machine learning. When you write, like few lines of code that creates your entire neural network design, then you definitely need some sort of compiler to compile it into, into a form that the machine understands and can train, it. So that's why you need a TensorFlow compiler. And we'll talk about there are many different TensorFlow compilers in a short while, right? So next, we want to fit the data. So fit the data is where what you guys probably know about training, right? Machine learning requires a lot of data to train. So you need to use run this line of code, model.fit, to train the X and Y so that your model learns and can be very powerful and accurate. The fifth one is you want to evaluate the model. Evaluate is like you want to test how well does the model perform. Okay, it's very simple. Now the last one is repeat by experimentation. So this one is like experimentation is where you created your model, right? And so what next? You created your model, but you want to test other parameters. Maybe, or if I change the number of hidden layers, it might perform well. So you want to repeat. You repeat the whole process with a different configuration only then you can see, oh, which one is it that it's actually very good, right? So this is a typical workflow for creating a neural network. Now, let's go into an example here. Okay, hold on a second, let me drink some water. I guess you guys should also take a quick sip. Okay, now let's start with a regression problem. So in regression, the idea is that you have some sort of numerical input, right? Let's say, you know, you want to see like, um, like, okay, for example, like you want to see the, uh, given the number of days, what is the predicted growth of a tree, right? Like for example, you know, like given 50 days, how tall a tree will go. So that is a regression problem basically. And in here, we have a house price prediction example. And in regression, the one that I just gave, right, given how many days, how tall a tree will grow, that is, you have only one input variable and one output. So that's a, you know, single variable regression situation problem. However, now we have a multivariate regression problem because our regression not only takes into account the number of bedrooms, but also the number of bathroom and the number of parking slot, right? So it's a multi-regression problem. And now what I want you to pay attention here is on the code, okay? On the code here, so here you have first, you need to create a model, right? The model, like I said just now, is the layers, the design of your neural network. So here you have tf.keras.input, the shape, because you have three input, you know, number of beds, number of bathroom, and number of parking slot. Then you will have number of, then your shape is three, okay? After that, you have tf.keras.layers.dense. 100 means you have 100 nodes, okay? In the hidden layer. And activation is ReLU. Now, we won't go into all the things that you see here that you probably don't understand, but we will go into some of them. And I think it's very important that, you know, you guys jot down some of the things. So right now, I think you can probably write down ReLU so that you can look it up later and learn what is it about. But for now, and also one thing that I want to probably bring out in, you know, it's a good time to bring out, and that is when you want to learn machine learning, you have to be comfortable not knowing some of the things, you know, and moving on, okay? You can't know like everything and, you know, be and expect to learn that way, okay? In machine learning is different. Sometimes you just have to be comfortable not knowing something and proceed with it, okay? So for now, you just assume that activation function is, you know, something that you don't have to know, okay? Okay, so we have here, you see three lines of the same code, which means that we have three hidden layers, okay? Three hidden layers. And then at the end, we have a dense layer, which is the output layer, if you know, don't already know. And the number is one, right? So why is it one? Because in regression, like I said just now, we want to predict the house price. And the house price is a scalar value, right? So you have 956,000, let's say, you know, this is the prediction, right? So it's a scalar value. That's why it's a shape of one, okay? And then, so after you have created your model, you want to compile the model. Just now in the workflow, like I have said, you want to compile the model and you have model.compile. And what I want you to really understand in compiling a model is that you have to define the loss function and the activation function. No, sorry, no, the loss function and the optimizer, not the activation, okay? Activation is the previous one, the creating the model. So what is loss function and what is optimizer? Okay, now in the loss function, a loss function is basically a way for you to tell the computer how far off the prediction is from the actual price of the house. Just like, for example, if I tell you, like you are a human being and I tell you, okay, say this house got 3 bedrooms, 2 bathrooms, and 1 parking lot. So guess what is the price of the house? Then you probably tell me, okay, let's say the price is 2 million ringgit. Okay, and I say, no, the price is 956. Or no, sorry. I mean, if you tell me the price is 2 million ringgit, then I will say, no, a bit lower. The price is a bit lower. So then you make another guess. Okay, the price is, let's say, 1 million. Then I say, okay, it's a little bit lower. Then you say, okay, 800. Okay, then I say, no, a bit higher. Then so this loss function is a way to tell the computer, like, okay, a bit higher, a bit lower, but in a mathematical way. Okay, and then so what about optimizer? So now you know what's a loss function. It's basically a way to tell the computer how to get closer to the accurate to the ground truth, to the actual price. So an optimizer is a way for the computer to go that path, to traverse the path. Okay, so for example, like, like let's say you have two people, and like one guy, when you tell him a bit lower, he might just say, oh, 1.8 million ringgit. But another person, he might say, oh, lower is like 50 ringgit. So to you it makes a lot of sense, roughly how much a price of a house should be, but to a computer it's not that intuitive. So an optimizer is an algorithm for the computer to uh, to do gradient descent. Okay, if you guys know what's a gradient descent, it's like when you plot a loss function, it probably looks like maybe I should just since I guess I can share my screen, right? So you guys can see the notebook here.
Yeah.
Yeah, okay. So like let's say I have a loss function and the price. You guys can see, right? Okay. So the higher the loss, the bigger the difference it is from the actual price of the house. And then like let's say I'm so sorry, right? I can't draw in the screen that I'm sharing you. So just bear with me here for a while. Okay, so like let's say here we have here, right, 500,000 ringgit, 956,000 and 2 million ringgit. And so if your model prediction is here, then if your model predicted 956, then it is spot on, right? Then the loss is basically 0 because the difference is 0. But let's say your model predicted 2 million, then the loss function tells the computer that, oh, the difference is very big and you should do some sort of correction. So now I plot some dots here. Now let's connect the dots and see how it looks like. Okay, so when you connect the dots, this is what you get. Okay, and if you guys probably know about calculus and differentiation, so this is where calculus comes in. And if you differentiate your loss function, you get the slope, the direction on where your next guess should be. So let's say you guessed 2 million, and then you do the loss function and then you calculate the slope of the curve, then you know that you should go to the left, right, to the left. So it's just like you have a ball and you want to roll the ball down the hill. It's the same concept, okay, in a sense. And an optimizer is basically a way to tell the computer, how fast should I roll down the hill, right? Should I roll down the hill slowly, or should I roll down very fast until a way that it might roll too fast and bounce back and forth and might never get down to the bottom of the hill. So that is some explanation on optimizers and loss functions. Okay. Now And then after that, after we have defined the loss and the optimizer, we want to and also this learning rate, right? So learning rate is like, you can think of it as how fast the computer learns, basically. How much the changes it should make at every iteration. And then the fit, the third one is fit. So you do model.fit, you basically, give the computer a lot of sample, a lot of data, and then it will try to fit a line for you, right? And epochs is the number of, times it will do it, 100. So this is basically a regression problem. And then now let's go to the next slide. So we have our cheat sheet here, right? I should have shown this one just now. You have the hidden layers, right? You can have minimum of 1 layers. If it's 0, then basically it's just it's just y equals to mx plus c if it's 0. But if you have more than 1, then it's more complicated. And you can have maximum unlimited number of layers, and neuron per hidden layer, which is this 100 here. Generally speaking, it's 10 to 100. Okay, there isn't like a formula to calculate on how many neurons you should do, but I mean there are some, but we won't go into it. Okay, but for now you can just generally it's 10 to 100. And then you have output layers shape, which is the shape, which is 1, right? The shape is just a scalar value, which is why it is 1. And then the hidden activation, which is ReLU, which stands for rectify linear unit. Okay, probably I'll say this is a homework for you to do at the end, is to look up what is rectify linear unit. Okay, and then output activation, don't have activation because this is a regression. Later we'll show you a problem which has an output activation. So I want you to see the difference. This is hidden activation, which is the activation layer for all the hidden layer. And then the output layer will have a different activation. In this regression case, output does not have any activation. And the reason why is because you want the value of the output, right? You want the price to be, you want to know the price, and the price is a continuous value. That's why there's no activation. If you have some sort of activation, then it might, but basically in this case you don't need one, right? We will show you maybe later on why on one example that you need. And then you will see here you have a loss function, right? And the loss function, okay, this loss function, just now I talked about loss function. And so when the computer says 2 million ringgit, and how you should do intuitively is that, okay, let's say you take 2 million ringgit minus 956,000 ringgit, and the difference is about 1 million something. And then you can either take the square of the difference, so that if your model predicted something lower or higher, it won't cancel out the value, right? So that's why you square it. Or you can take the absolute error, or absolute is also another word for modular. You take the modular so that all the negative difference becomes positive and the difference adds up. Okay, and so MSE, mean square error, MAE, mean absolute error, and at the end you have optimizer, so stochastic gradient descent, SDG, or Adam optimizer. Optimizers, there are a lot of optimizers, okay, throughout in the past few years, or a lot of research has been done on optimizer. You have all sort of techniques. However, for loss function, it really depends on the situation, on the problem they are trying to solve. If it is a classification problem, the loss function is usually that one of loss function. But there's many types of optimizers. Okay, SDG, SGD, stochastic gradient descent, Adam optimizer. We won't go into exactly the optimizer for each one of them, but you just have to know what's an optimizer. Okay, now let's look at the classification problem. So just now we have a regression, a numerical X input, and an output that is also a numerical value. In classification, things gets a bit different, because now let's say for this example here, you have a image as an input, which you can also think of it as a numerical value, because all the images are going to be changed to tensors, and tensor are just numbers. And then the output, instead of a number, now it is different classes. This is the difference between regression and classification. Instead of numbers like a price of the house, you have three classes. Either is it a sushi, or is it a steak, or is it a pizza? So these are the difference. Okay, now I want you to see here, like for the model wise, the shape 224, 224, 3. So 224 is probably the number of pixels on the x axis. So this is probably the square picture, right? 224 pixels, x and y. And then 3 is because there's 3 channels, R, G, and B. And then you have so this is the input layer. And then you have the tf.keras.layers.dense, which is the dense. So in this case, you only have one hidden layer. And then after that, you have an output layer. So in this case, instead of 1, you have 3, because you have 3 classes that you want to predict. Okay. Okay. Now activation function, softmax. This one will go into detail. Okay. I want to show you one example of activation function, so that sort of a sense on what activation function is and how powerful it is that make machine learning where it is today. Okay, now we want to compile the model after that. So just now, if you still remember, in a regression problem, the loss that you use is a mean absolute error, MAE. But then in classification, it is a categorical cross entropy loss function. So just now the MAE, it is easy to understand, right? 2 million minus 956,000, the difference, you remove the negative if there's a negative, and you find the mean, right? You add them all up and you find the mean. So that is intuitive. But what about cross entropy? Cross entropy is a bit more complicated, and I guess we probably we won't explain in depth, but how the function looks like is that, picture a log function. Maybe I will draw it now. Okay, maybe I will just write it down. Okay, hold on a second. So do you guys still remember your log function? Log function, right? Is this how a log function looks like? So this is 1, right? This is 1, and this is your log function. And when you take the negative of the log, then it looks something like this, right? Is that correct? Something like this, negative of a log function. So cross entropy is basically a negative of a log function, and you guys can look into it, if you want. But we won't go too much in depth for this one today, cross entropy. And the optimizer is Adam optimizer. The reason is because I think the previous optimizer is also Adam optimizer. Actually, a lot of Adam optimizer, I think at this point in time, is the best optimizer out there. Okay, and it basically builds on top on previous techniques like stochastic gradient descent. Okay, you have stochastic gradient descent with momentum and RMS prop. You can write it down, RMS prop. I think if you write it down, you can look it up later. Each one of them, I think, builds on top of each other, and Adam at this point is the best optimizer out there. And then you just like just now, you need to fit the model, give it a bunch of data and the correct answer, so that it learns, machine learning, and then you evaluate the model. Okay, and then so the output in this case, instead of just one number, it is a sushi. I mean, it is a tensor with like more than one value, more than one number, right? So you have 0.93, which probably is the class for sushi, and 0.13 is probably a class for steak, and 0.236 is the class for pizza. So the number that is the highest means that the computer is the most confident that this class is sushi, right? And here's a cheat sheet. It's basically the same thing like I said just now. The difference is that the loss function is a cross entropy loss, and the output activation. Now this case there's an output activation. Just now there wasn't an active output activation. Now there is an output activation. Now I want you to pay attention here. There's binary classification and a multi-class classification. Multi-class classification means that you have more than 2 classes. So like 3 classes, like, right? For example, like dog, cat, and turtles, 3 classes. Binary classification would be just dogs and cats. And the reason why the output activation is different, in this case, it says sigmoid for binary classification, and multi-class classification as softmax. That one is very important, and we'll touch on it in a short while. For now, is there any question any one of you would like to ask anything? I guess this is a very good time for question because a lot of them are very complicated, and I just think that some of you might have any question because we do take into account like question time. So if you guys don't ask any question, we might end a bit early. So don't worry that you might take up some time. You have already taken into account question time. Any questions? Okay, I guess no questions. If you have question, and you can put it in the chat box, or you can just unmute. Okay. Okay, now I think it's very important to get the fundamentals right. So what we have now in the next 10 minutes is that we're going to do a graph to show you exactly what am I talking about with softmax and sigmoids and all those things, right? So okay, now let's go to the beginning. Okay, in this case, now we have here, you guys can see, right, 3 colors. Sorry, 4 colors. This is red, this is orange, this is green, this is blue. And you can think of it like, just now in the example here, you have like 3 classes, right? One is you have like 3 classes. One is sushi, one is steak, one is pizza. And then now we have 4 classes, and the idea is that the dot that is further to the right hand side, which or in other words, the class that has a greater numerical value, the computer is more confident that the input is this class. So for this case, let's say the computer predicts like the value is negative 1 point something, and then this one is 0 point something. Then it thinks that this blue color class is it thinks that it is the most likely one. Okay, now what is softmax? So softmax is like I said just now, is a tool for you to use in multi-class classification, right? And so why softmax? So softmax, like let's say I give you a scenario, right? Okay, a scenario is that let's say the computer, before the softmax activation function, before the softmax, let's say I'm the computer, and I think that you give me a picture of sushi, and then my output before the softmax activation function, my output will be okay, for the for the sushi class, I think it's 100. Okay, what do you mean by 100? So it's just a value at 100, and then the sushi, the steak class is 300, and then the pizza is 500. So 500, right? 300, 100, and 500. And then if you feed me another picture, let's say the second picture is a picture of a pizza, And then now my prediction, my model before the activation, softmax activation function. Okay, I think that sushi is 10, pizza is 20, and steak is 50. Okay, so you see the difference. Just now it was hundreds and now it's tens. However, the actual value doesn't matter, right? What matters is the difference between the classes, okay? The relative difference in each pixel. And that is what softmax function essentially try to solve. It normalizes it, it scales it down so that when you add, like, so the formula is basically, I mean, to simplify it, the formula is actually more complicated. You can think of it like, let's say the output is before the softmax function is 10 plus, is 10, 30, and 50. You add all of them up together, and then you take like so that you can calculate the probability for, let's say the sushi class is 50, and then 50 divided by 10 plus 30 plus 50. So there is a probability that the computer takes. Okay, so now regardless of the output before the softmax, even if it's 1,000, 1,000, 3,000, 5,000, it can still scale it down into a probability. So that is the general idea of a softmax function. Okay, so now with that in mind, so now we have our four classes, and a softmax basically uses a e to the x. So you have this e to the x function here that I have shown you in this graph here. So this is e to the x, and it basically, first of all, it maps all the classes to e to the x. And if I press here, you can see, right, this is mapped to here, mapped to here, and mapped to here, and mapped to here. And then after that, I get this graph. So this is basically like, this one is the sum of all these four, right? Okay, and you can just think of it like this is your one, okay? And basically when you calculate the probability of the class being chosen, is like, let's say you want to calculate the probability for the blue class, then it will be the height of the blue class divided by the sum of the total. And so what is different from this one than what I've said just now is that just now the one I said does not have exponential function, right? This one got exponential function. So when you add exponential function, if you increase one value, let's say this blue color, if we increase just by a little bit, it changes a lot. It increases exponentially in terms of the probability, in terms of its probability. Okay, if you can see here, let's say I just move a bit. Okay, so this one, like, it's like half, right? Right now it's half, but if I move a bit to the right, then immediately it becomes like, just so much, or just a larger portion in general. And if I move to the left, then it gets very small very fast. So this is a characteristic that I hope that with this Desmos tool, you can visualize the softmax function. It has an exponential element inside of it. Okay, and just now, like I said, if you have 1,000, 3,500, 5,000, it's the same as 10, 30, 50, because when you shift, like when you shift this, it basically, okay, actually I should run this one first. This squash one is, what is the difference between this and this is that this one keeps the total height the same. So when I change, this one, the total height changes, but this one doesn't, so that you can really see in a different sense. Okay, when I move the green color one, you can see how fast the other one gets squashed down. Okay, so this is the feature in exponential that you get. And now when you see I shift, this shift is basically let's say you add 1,000 to all the values, right? So 10, 30, 50 becomes 1,010, 1,030, 1,050. when I do that, you realize at the bottom graph, it doesn't change, right, the total height or even the individual, like each classes. So that is, one thing about softmax, which is why it was invented and used in the first place. Now, the second one is very important that I want you to pay attention, and it's called okay, which is this multiply. So if you add or minus, no change. However, what happens when you multiply or divide? Okay, this is very important. Okay, um, and the reason I say it's important because I want you to pay close attention now. If I multiply, what do you see? You see that the 4 points spreads out, right? And if I, multiply it in the like fraction, if I multiply fractions to it, then it clumps together. So in machine learning, this is called temperature. Okay, probably you want to write this down. Temperature in machine learning is a parameter that you play with so that you can tune your model to be more either deterministic or more random. So let's say if I shift the, if I multiply, right, I multiply all the value such that you can see it got spread out and it becomes, is this more deterministic or is it more random? It should be more deterministic because now, like this class dominates the probability space, and this is more, becomes more deterministic. However, when I multiply it in the other direction, then it becomes more random in a sense that all the classes now are about the same in terms of its probability, right? So this is one thing that I want you to take away from here. And this is softmax function. So temperature, right? I talk about temperature, deterministic, randomness. If you search GPTJ, okay, this is a natural language generative model, right? And you can see here temperature. So this is where, a good example on what temperature is in machine learning. Okay, I've explained it to you and I give you a concrete example on the use cases. So if you change the temperature here into a larger number, then it becomes more deterministic. The result will be the same if you run it multiple times. But then if you reduce the temperature, okay, I think I can maybe show you example here. Like, let's say if I have a very low temperature and I run the model, then what I should predict is that the output is not the same every time I run the model, right? And then when I run it again, then it technically shouldn't be the same. Yeah, okay. And if I have a high temperature and I run it, then it should be sort of the same. It's not like yes or no, right? In this case, because the temperature, but it's this concept, okay, that I want to bring to you, okay. And now, since we have, I think it's now, okay, I still have 5 more minutes. Okay, now the next 5 minutes, I want to tell you about this one. So we talk about multi-class classification. The output activation is softmax. So what about the binary classification sigmoid? This one is also very interesting in my opinion. Let me just open up a picture for you. Softmax, this is sigmoid, right? Sigmoid. Yeah, I think you can see this picture here. Okay, this picture is what a sigmoid function basically is, right? And you have many types of, no, it's actually not many types, it's just different function. Only one of this line is a sigmoid function, and it's this 10h line, okay? 10h is the function for sigmoid, and the rest are just different functions that looks very similar to the actual sigmoid function. Okay. And now the question comes up, right? Why do we choose 10h as the sigmoid function? Actually, the sigmoid function, the formula is, maybe I can write it down. I think it's not in the slide, but the formula is 1 over 1 minus e to the x, right? This is the formula. Or in another way, you can also write it, if you multiply the numerator and the denominator by e to the x, then you should get e to the x. I think it's like this if there's no error. Okay, so both of them are the same. This is a sigmoid function. And now the question comes, right? Why do we use 10h, which is this green color line? If you can see here, green color line. Why do we use this one instead of other functions? And the reason is actually very interesting, right? The reason is because when you do the loss function for 10h, actually, I think I should show you guys the softmax one. So maybe I can, in this function, it all comes down to the loss function. Okay, when we have a like the 10h, like let me type here 10h. When you want to find the negative log, and what is the negative log again? No, actually, I think there's a mistake here. I mean, what I'm trying to say is that you can probably play around with it after this, but the idea is that when you have actually, where's the picture? I should open the picture up. This picture here. The idea on why you use 10h instead of all the other function is that when you calculate the loss function, the gradient that it shows is actually the best that you have, which is very important in machine learning, right? Um, and yeah, I guess that's 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 all I have for now. So right now it's break time. We have about 5 minutes for break, and yeah, I guess, yeah. If you have any question, you can also ask me now, or else we'll see you guys in 10 minutes, in 5 minutes time, which is 9:15. We'll continue in 9:15.
All right, guys. So now in the next hour, you will learn on how to build a neural network in TensorFlow in depth, and also you will learn how to create a CNN and actually let's yeah, you will learn how to build an animal classification model that is trained with efficient net B0. This is the app right here, and the model power behind is basically created from TensorFlow. Yeah, this please stay tuned to the end of this session where you will train a neural network that can classify 90 different animals. Yeah, let's take a look. So if we import the images of fox right here, and then we predict, and it will return a fox. Yeah, this is what we are going to cover in the next hour. And yeah, stay tuned. So for the collab notebook, and yeah, this is what I'm going to cover. And then this is basically the modeling step in TensorFlow. So first, you will need to create a model by defining the input, hidden, and the output layers of the deep learning model. This is basically a neural network. And then you will need to compile a model by specifying three matrices, three hyperparameters, which is loss function, and an optimizers and an evaluation matrix. So for the loss function, it is basically tells our model how wrong it is. And then for the optimizer, is basically tell our model how to improve the patterns by learning the weights and by adjusting the weights and biases. And then for the metrics is what we can use to interpret the performance of our model. And then finally, we are going to feed our model with a lot of data to actually help our model to figure out what is the best pattern between the X and Y, which is features and labels. And then let's take a look at this example right here. So how to create this neural network in TensorFlow? We are given the input layer with four neurons, which is sepal length, sepal width, petal length, and petal width. We are asked to classify which flower it is, which is Sentosa, versicolor, and virginica. So by fitting in these four inputs, four features, we are going to classify which is the flower, which type of the flower it is. And then let's create a more neural network with sequential API. We first defining, let's just zoom in. Yeah, we just initialize the model with tf.keras.sequential, and then we pass in a list of layers. So in TensorFlow, the layers is defined as this. And then dense layer is actually the fully connected layer, which is commonly used in TensorFlow. So this is our first hidden layer right here, which is this layer. And then we assume that we have 10 neurons right here. And then our activation is ReLU, and then input shape is 4. So if you don't pass this input shape right here, you can actually pass in the front tf.keras.layers.input right here. And then we pass in the 4. So this will actually is the same as the input shape equals to 4 with this layer right here. Let's just import TensorFlow STF. and then we run it. So this is how we define the layer of this neural network. And then the third layer, which is the second hidden layer, we have 10 neurons, and then activation will be ReLU. And then the output layer will be 3, because we have 3 classes right here. And then we can see our model via model.summary. And then this is going to give us a detail of each layer. And also we can define the layers by using our functional API in Tensorflow. So this is basically, this functional API right here is basically same as this sequential. So let's just break down it. So we first say that the inputs is equal to tf.class.input, and we pass in the shape. Actually, we can remove this right here to become 4. Yeah, it is the same. And then for x is equal to tf.class.layers.dense, and then we pass in 10. Activation will be ReLU. And then we pass in the previous layer by stacking it up. And this is going to be at the right hand side of the next layer, which is this input is over here. And then we also reuse the x. Yeah, x equal to tf.class.layers.dense equals to 10. Activation is equal to ReLU. And we pass in the previous x at the right hand side. So for the outputs layer, we have 3 right here. This is over here. We have 3 outputs, the outputs neuron, and then we just define the model equal to tf.class.model, and then we pass in the inputs, which is this one right here, and then the outputs will be all the layers, yeah, including the x. So we run it, model.summary, and then we actually get the same model as this sequential model. But in this case, we can see that there's an input layer right here, but it is more or less the same. If you train the model, it will actually yield the same result. So the question is, what is a dense layer? Simply just a typical fully connected layer. So you can actually go to this link right here to read into detail of what is dense layer. And then after we defining the model right here, there are 2 ways. Yeah, we can either define it in sequential way or functional way. After we define the layer, we are going to compile the layer by specifying three hyperparameter here, which is loss, optimizer, matrix. Yeah, and then we are going to fit the model. I'm not going to run this. This is just an example. And then now let's work on a small regression example. So for the typical ML problem, we will need a lot of data to actually produce a good model with accurate result. So in this case, we are just going to create our own data. Yeah, create the data by importing NumPy and then import Matplotlib. And then we create our features. So our features is basically x equal to MP array. We have a list over here. And then we create our own label, which is this right here. So as you can see, if we visualize our graph over here, it will produce a straight line. And as you can deduce from this x and y, this -7, if we plus 10, is actually equal to 3. So if we plus -4 plus 10, it will produce 6, and then so on and so forth. So we can deduce from these features and label right here in y equal to mx plus c. Yeah, so y is actually x plus 10. -7 plus 10 is equal to 3. Yeah. So if we run, it will actually become all true. So now we have our own data right here, and we want to use this data to create a neural network. So now we define the model first. Yeah. Before that, we set the random seed to basically keep the weight and biases initialization be the same for all the time. Yeah, tf.random.set seed. This is basically same as the Scikit-Learn random state. So 42 is a universal value for random seed, and you can set it with any other numbers. So model 1 equal to tf.cross.sequential, and then we pass in a list right here. So this is our input layer, which is in one neuron, and then this is our hidden layer. Sorry, this 3 layer is our hidden layer, and we can pass in whatever value you want. And this is our output layer. And then you can actually define the layer by this method right here. So the first is actually define the sequential, and then we add each layer one by one. I will prefer this method right here because it is quite easy for me. And then we proceed to compile the model. Then model one dot compile, and then we pass in 3 hyperparameter here. So the first one, loss, we are using tf.cross.losses.mae. You can use MSE. This is coming from the slide right here. So if you are dealing with regression problem, you are typically going to use MSE or MAE or Hoover. Yeah. So you can pass in MAE right here, or you can actually pass in MAE like this. This is the same as the previous one. So for the optimizer, we are going to use stochastic gradient descent. And then for metrics, we can pass in whatever value in it, like MSE, MAE, in a form of list. Yeah. So we feed our model with the data with 5 times. So as you can see, this one is the training process of our model. So we get the loss is actually 12, which is pretty huge right here. So we want to get the loss function that is less than 1. Yeah, as small as possible. So this is the exercise for you to try it out to make this loss become less than 1. Yeah. So let's do some prediction with our model. Let's say we pass in 17 right here. The model will actually give us 7, which is wrong, right? Because our formula is x plus 10. The result will be 27, but our model only give us 7. Yeah, so you can try to create a model with less than 1 loss and less than 1 MAE. So now let's take a look at a larger example right here. We are going to build a multi-class classification model. So first, this is basically the explanation of multi-class classification, which is more than 2 class. So if you have dog and cat, it's binary classification. And if you have dog, cat, turtles, it will be multi-class classification. So to practice this, we are going to build a neural network to classify image with different animals. So the data we are going to work on is coming from Kaggle, which we will get 90 different looks like it's connection problem. Get our data right here. Let's just wait until it finishes. So we are going to build a neural network to classify 90 different animals by this Kaggle dataset. So after we get our data, and then it will actually give us the archive.zip in this Google Colab VM. And then we unzip the archive.zip. So after unzip this, and you will need refresh, and then you will get a folder called animals, and then inside the animals we will get another folder as well called animals, and then in this animals folder we will get lots and lots of different animals right here, and then in each folder we will get 60 image file right here. So yeah, this is one of the example of the image, which is antelope. And then this is the animal. And then we are going to work on this data set right here. So now we have our data ready, and then we want to load the image data into tensors. So this is how a typical workflow on how we can load the image data into tensors. So let's just re-import the TensorFlow, and then we actually need to define the directory of the image right here. So this is the root directory for all the image class. We have 90 class, and then we just need to copy the path right here, and then we just need to pass in like this. So in Google Colab, you can actually eliminate this content right here. It will actually produce the same result. So we are going to use tf.keras.utility.image dataset from directory. This is the method to load the image for us easily out of the box, and we can actually pre-process the image into the image size we want. In this case, we are passing in 224, 224. You can actually pass in whatever value you want. Yeah, you can pass in whatever value you want, but I just pass in the value that is divisible by 8. Yeah, so first we need to pass in the directory, and then the batch size. The batch size here is basically we are specifying one batch is equal to 32 image. You can pass in 64 because we want to train our model using a batch of images, batch and batch of images. So this is the image size. And then for the subset, we are going to pass in training. This subset and validation split comes together. So if you pass in subset, you must pass validation split. So if you pass in training right here, you are actually going to pass in a smaller value, which is 0.2, because in this case, we want to produce a data set which is in 80% of images. So this will actually produce the image with, the image with 80%. So the seed is actually the how we actually, yeah, this seed is basically will be same as the validation data set right here, because we don't want to mix our image data set. So everything will be the same unless the subset will be validation, and then the validation split will be 0.2, which will produce 20% of the validation data set. If we run this, oh, we can't put like this. So let's just rename it. So sorry about that. And then we actually produce 80% of image for training. And then we produce 20% of image for validation. So let's just see our train dataset and validation dataset. So the dataset comes into batch dataset right here. So the first value right here is actually the batch size. The 224 right here is basically the x-axis of the image, which is the width of the image. And then the 224 right here is basically the height of the image. The 3 is the RGB. We have red, green, and blue channel. So this over here is our image. And then this none with a tuple right here is our label. So it comes out of the box and pre-process the image for us by labeling our image with classes. As you can see, this image right here will basically is this format tensor, and then the antelope will be pre-processed out of the box for us right here. And then let's get the class name of our train dataset. So this is basically the name of the folder right here. And then we can actually optimize the performance of data fetching during the training. So we can actually prefetch the dataset, actually turn the batch dataset into the prefetch dataset. So previously it was batch dataset, and then now it will be prefetch dataset. And then this tf.data.autotune is basically coming from the official docs, TensorFlow official docs. And then this is telling the TensorFlow to go ahead and get the best value for us. Yeah. So after we optimize the performance of the loading speed of the data, and then now we are going to visualize the data right here. We are using plt.imshow to show our image right here. So actually this is coming from the TensorFlow guide. You can go ahead and look for it. And then we have tiger, which is this image, and then antelope, and then orangutan. And we have a lot of image. And we are going to use this data to fit into our model for training. Yeah. So let's see one of the image on how they represented in Tensor. So actually, yeah, this is the gorilla right here. This image is represented by these tensors right here, tf.tensors. They are actually 224, 224, 3 in shape. So the first one will be the width right here. And then the second one will be her height. And the third one will be the color channel. So for the first pixel, as you can see right here, we have R, G, and B. So for the first value will be 26. The second value will be 23 and 16. So for the image, the first pixel right here, you can see, which is about like black color. So this is basically near to 0. Yeah, this is how we numerical represent an image. Yeah. So now let's actually comes into the highlight of this today's session. We are going to build a multi-class classification model, which is going to perform very well if you are using CNN. So now, what is basically CNN? CNN is proven to be work in a lot of image problem. So CNN is the short form for convolution neural network, and we are going to take a look at what is it in later. So let's see some of the parameter we want to use. So we have load the image dataset into the input shape of 224, 224. And then for the output shape, we have 90 because we have 90 class of animal. For the output layer activation, we are going to use Softmax because we are dealing with multi-class. If we are dealing with binary classification problem, we are going to use Sigmoid. So for the loss function, we are going to use the sparse categorical cross entropy. So if your label is actually one hot encoded, you can use categorical cross entropy. But we load our data by using the tf.curves.utils.image dataset from directory. It is basically coming from label encoding. So it is not one hot encoded, so we are using sparse categorical cross entropy. For our optimizers, we are using tf.curves.optimizers. So this loss function and optimizers and output layer activation, you can actually search from the cheat sheet right here. We are dealing with multi-class classification. So we are going to get the softmax at our output layer. And then we will need to compile it with the sparse categorical cross entropy because our label is not one hot encoded. So for the optimizers, we usually use Adam. Yeah. So for metrics will be accuracy. So now let's take a look. So this is typically the CNN. So we have the image right here. We are going to pass in into each of the layer, and then it will actually produce an output. So in this case, we are using animal. So this is coming from the internet, and a typical CNN will actually have a convolution layer and followed by pooling layer. Some of the CNN will comes with 2 layer of convolution and then followed by a pooling layer. So it's actually repeated 2 times, and then we are going to flatten it, and then we are going to pass in it to the output layer with softmax activation. So this is how we actually define the layer of the CNN. So model 1 equal to tf.curves the sequential, and then we pass in into a list of layers. So the first layer will be the input layer, which is the shape of the image 224, 224, and 3. And then the second layer will be the conv2D layer. So this first parameter right here will be the filters. Oh, sorry. Will be the filters on how many filters we want to actually filters our image. And then for the kernel size, it's actually the square of the size 3 by 3. We will take a look later on this right here. And then followed by the max pooling layer. This max pooling layer, we will cover it in the slide as well later. And then we follow by another conv2D and max pool layer. right here. Our activation will be ReLU. Yeah. So we are going to flatten the outputs of the max pool right here, and then we are going to pass into the last output activation, which is Softmax right here. The output layer we have 90 neurons. And then now we shall take a look at what is actually the Conv2D layer. So basically a Conv2D layer is like this. We are not going to cover the underlying formula. So we just need to visualize on how actually the Conv2D layer works conceptually. And then for the input image right here, we are going to pass into the Conv2D layer, which is the filter right here. Yeah, the filter. So this is actually the kernel size. Yeah, 3 by 3 kernel size. So the output will be actually 16. It's actually coming from the model learning pattern. Yeah, we are not going to specify each of the single numbers right here. This is going to cover by the model training. During the model training, it is going to actually figure out the best pattern, the best numbers for each value right here. So this is actually the filters, and then we specified how many filters we want. And then the kernel size right here, which is 3 by 3. As you can see, after we filter our image right here, we will get a 3 by 3. This is actually the 5 by 5 input image, and after we filter it, we will get 3 by 3 output. So it will actually remove the first and last of the edge. It will actually remove the edge right here. So if it's 5 by 5, and then it will become 3 by 3. If it is 6 by 6, it will become 4 by 4. It will actually reduce by 2. So this is actually how the Conv2D layer works. Extracting the image right here, and then figure out the best feature in it. So for the max pooling layer, it is going to shrink the image down. So we are taking this as an example, and then we have 4 by 4 input image, and then we are using 2 by 2. By default in TensorFlow, we are using 2 by 2 max pool layer. So actually, this is a 2 by 2 in size, and then we are going to output the maximum value in this 2 by 2 box right here, and it is 20. We will get 20 right here, as well as this we will get 30, and then 112, and then 37 will be the max. And then this is how actually the max pool layer works. We are not going to cover it in detail on the formula side. We just get some intuition on how this layer works right here. So for the image problem, we are using the CNN. Normally, you will see in action they are defined like this. And then you can search for more information in the internet. So after we talk about the Conv2D and max pool layer, what is the flatten layer? So let's just run this. Yeah, we will get the Conv2D layer. As you can see right here, the Conv2D layer is actually reduced by 2. Yeah, previously it is 224, and then this will reduce by 2. And this will reduce by 2. And then 32 is the filter of this. Filter of the Conv2D layer. And then after we passing into the max pool layer, we will get we will divide by 2 for each feature, as you can see right here. And then after we pass in into another conv2d layer, it will actually reduce the 111 into 110. It will actually reduce by 2. And then max pooling layer divide by 2. And then flatten layer is actually will come out with a result, which is this right here. It's coming from the multiplication of the previous, the previous output. So we are going to use the dense layer for our output layer for, which is 90 different classes. And then after that, we will need to compile the model by specifying the loss, which is sparse categorical cross entropy, and then the Adam optimizers. And then for metrics, we are using accuracy. So this is some of the reference for you. By the way, our neural network actually prefer the data to be scaled or normalized, which is between 0 and 1. So in this case, we are going to add in one layer after the input layer, which is layer.rescaling. And then one pixel value for one RGB color, we will have 255, 0 to 255 value. So we are going to actually scale the tensor's value between 0 and 1 by this layer right here. And you can see the rescaling layer in the TensorFlow official docs. Now we will feed our data with trained data set, and epochs we are going to use 5, and then validation data. So you can fit the model right there. So it's run pretty fast because we are using the what we call GPU right here. Colab actually provide a free GPU for us to use, so you can actually use it. So as you can see right here, our accuracy is going up pretty fast from 0.05, from 5% of accuracy to 37. So we just fit for another 1 epoch. So as you can see, the accuracy right here will be 0.38, and then for the var accuracy is 0.15, which is make a sense of underfitting right here. So the loss function, the loss will actually reduce. So we can fit more. One last epoch. Let's go. So actually, during the training, the accuracy is pretty high, which is 92%. But for validation, during the validation period, it will actually give us the result, which is pretty low right here, which is 24. And you can actually improve the deep learning model by all 8 steps right here. But we are not going to do that. We are going to use transfer learning and fine tuning right here. So what is transfer learning? It's a method for us to use a pre-trained model that proven to be work in real life, and then we use that model in our own problem. So surely someone has spent time crafting the right model for the right job. So the typical workflow for transfer learning is basically taking the layers from the previously trained model, and then we actually freeze them to actually freeze the weights of them. So to avoid destroying any information they contain during the future training rounds, we can freeze them by actually using the model.trainable equals to false, and then we add some new trainable layers on top of the frozen layers. This will actually be our output layer by specifying the how many classes we want and the softmax activation. And then for the fourth right here, we want to train the new layers on on your own data set. And then actually for transfer learning, it will actually come for one more step right here, which is fine tuning, which consists of unfreezing the entire model you obtain and retrain it with the new data. We will actually unfreeze out, some of the top layer, and then we feed it into our own data set. So this will greatly improve our model performance and accuracy. So you can see the guide for TensorFlow right here for our transfer learning task. And then for the popular image pre-trained model, we have many kinds of neural network. So we are going to take a look at EfficientNet right here. And you can explore more in TensorFlow Hub, which is a pretty good platform for you to get a pre-trained model. And let's just run this cell to get our EfficientNet. tf.curves.application EfficientNet B0. So we have B0 to B7, but in this case, we are using B0 because B0 is very simple and B7 is very complex, and it is a very big file right here. And we are passing the include top equals to false. This is going to actually don't, yeah, this will not give us the output layer. So let's run this cell and we will get a pre-trained model right here, which is called as EfficientNet. And you can load the model from TensorFlow Hub like this. And then let's see the layers inside the EfficientNet. So we have 237 layers in it. So we are going to use this pre-trained model to run on our own task. So let's check if the model is freeze. So if it is true, it's actually unfreeze. So we are going to freeze the model. EfficientNet.trainable equals to false. So this right here will actually unfreeze the model. Yeah. And then we define the model by specifying the input layer right here, and then the EfficientNet, which is the pre-trained model layer. And then we passing the global average pooling layer. This layer will actually help to convert all the tensors in actually 4 dimension into 1 dimension. Yeah. So for the last layer will be layers.dense. We are going to pass in 90 and then activation is softmax. So we actually use sequential. You can use functional API as well. This is similar to this right here. Then we print it. So we get our model. We actually get 3 dimension right here. But after we pass it into the global average pooling, we will get 1 dimension right here. Yeah, so we proceed to the compilation. Yeah, so we fit our model. So I'm not going to do that since our time is limited right here. You can run it as well, and this will produce a very good result. Yeah, I'm not going to run this. Yeah, for fine tuning, it will actually, let's see the layers right here. We have 2, 3, 7. So for fine tuning, we will actually unfreeze the top layer, some of the top layer right here. Yeah. Efficient net dot trainable equals to true. This is going to unfreeze equals to true is basically unfreeze all, and then we pass in this line of code here, which is going to freeze the top 200 layers. And then as you can see in the layers section, yeah, we can visualize it. So the first layer until the 200 layer, we will actually get false because we freeze them. And then the last 37 layer, we will get true value, which is, yeah, it will actually change the weight of these 37 layers. And then we can compile the model right here. And then we fit the train dataset into the model. And in this time, we are using 10 epochs. And then the initial epochs, we are going to pass in the 4 right here. This is actually the 4 coming from the previous model training. And then we train, we train based on the previous model. And then you can pretty much run this. Oh, we actually don't have this code right here. You can run the previous cell right here, and then you run this. And then we can actually evaluate our model by passing in the validation dataset into evaluate. So in this case, we are not going to cover this because, yeah, let's just try the first model right here. Model 0. Oh, wait. Let me see. Yeah, model 1. Let's just, because we have our model 1 fit it with the data, we are going to use model 1 to visualize the accuracy right here. In this code, you can actually read by yourself. It is pretty straightforward. Yeah, this is how the model 1 perform. So which is pretty bad. If you run the model 2 right here, you will actually get a pretty good result over here. So the true is actually hare, but the model predict it is butterfly, which is pretty unlogic right here. The true is hamster, but it's actually predict bee. So you can actually try on with fitting the model 2. All the code is in the collab. Yeah. And then you can try it out by running this cell with model 2. All right. So you can test your model by passing in the URL for this image right here. Yeah, I'm going to pass in model 1 because our model 2 is not ready yet. So we predict the image. which is pigeon. Let's see this image right here. This is actually a fox, right? But it predict pigeon, which is very inaccurate. Let's take a look at how we can save the model. There are two types of format right here, which is save model format and then H5 format. You can pretty much do like this in one line of code to save the model in save model format, and then H5 format, you can actually pass in .h5 right here. Yeah, you can also load the save model by using tf.keras.models.load model, and then you passing it the file path of the model. So this is basically the extra that you can take a look on, which is TensorBoard. This TensorBoard is actually a way for you to visualize your model performance. So I'm not going to run this cell. You can try it yourself. So if you are working on JavaScript project, you can export the model into TensorFlow JS model to be consumed in the JavaScript like web framework like React or Next.js. Yeah, this is pretty much it for the collab session. And you can actually run the cell right here. I have no time to run. Yeah, you can run this cell. You will actually get a pretty good result. Yeah, so let's go back to Yongsu. Thank you.
Thank you, Ziqing. Yeah, so I hope that was a very interesting and insightful collab session. And so I guess we have come to an end for today's session. And before we end, right, I just want to show you guys, some of the fields in machine learning that it's worth exploring, right? So where to go from here? After you have taken about 4 sessions and learned some of the basic, uh, there are some pathway that you can take in your ML career. So the first one is, I guess, talking about TensorFlow specific thing. And that is, just now I talked about TensorFlow model compilation, and there are many ways of compiling TensorFlow. Okay, you have the main method, which is the one that me and Ziqing have shown you, and you have a different method, which is called the XLA TensorFlow. So this is a modified compiler, and what it does is basically you can see here XLA stands for Accelerated Linear Algebra, and it's a different compiler that is a very domain specific one. Okay, and this is people use this compiler because the time it's way faster. Okay, it's just a faster compiler. So this is something that you can look into that is TensorFlow specific, since our session today is about TensorFlow. And then the next one is about machine learning in general. So, we talk about CNN, right? And there are other things as well, like RNN, LSTMs, GRUs, that you can take a look and try to learn. These are the architectures. And also variation autoencoders. So it's like, encoding and decoding, but in machine learning. And then transformers, right? So just now I show you LSTM. So LSTM is like I think it was first published in the 1970s or 90s. And Transformer is just newly introduced in 2017, and it's very powerful. And you can see the complexity as well from this picture that I have here. Is it looks scary, but it's actually not if you understand it. And then after that, you have graph machine learning, which is also a field that you can explore. It's very popular now. And then after that, you have reinforcement learning. This one, I guess, is pretty common and widely known. So it's reinforcement learning. And then GANs, generative adversarial nets, I guess this field is getting more and more interesting since I think in the past few months there have been huge development in this domain by NVIDIA. And for example, I have this picture here is basically, I think, built by NVIDIA, one of their most recent work. And that is, you just draw a few lines and it can, come up with a beautiful picture for you, right? So huge, improvement in GANs and definitely worth checking out. And then we come into more, very hard machine learning. So quantum machine learning, I would say, is a very new field. If you are interested in quantum computing and machine learning, you might consider this. It's very technical and rigorous. So yeah, I guess it's the same for most physics topics. And then another one is ethics in AI, right? This is something more on, I guess, less technical, but it's getting increasingly more and more important as we move into a AI-driven world where a lot of things like ethic needs to be worked out. And I guess if if this is something you are interested, you can probably explore some of the work that has been done in ethics for machine learning AI. And so let's talk a bit about career planning, right? So how should you choose your pathway for your machine learning career? So I would say there are generally three domains that you can choose one to focus on. In machine learning, I'm talking about commercial machine learning, okay? It's not academic research setting. So in commercial machine learning, you have three domains. The first one that you can see here is predictive analytics or predictive analysis. So it's something to do with prediction, something to do with predicting the future, time series analysis in general, okay? So that's the first one. The second one is text to speech, speech to text, or speech, or more commonly known as natural language processing, NLP. So that's the second one. And the third one is image recognition, machine learning, vision. So it's under the area of computer vision. So when deciding which domain to focus on, it's more of what are you interested in, and also it's okay to have more than one. Sometimes some of the as machine learning gets more and more common, sometimes you don't just only use one, right? You might need to use two of these three domains to do what you're trying to do. But this is just a slide to show that what are the options out there and what you can choose to focus on. Definitely choose not definitely my advice is to not focus on all three, because uh, it's not the best option. You know, this is I guess my opinion. um, and so we will end our today's session with a meme. So I guess you can look at this meme yourself and uh, laugh at it. And yeah, I guess that's all from us today. We still have like 2 more minutes, 1 more minute. And if you have any question, I think now it's a really good time. And also, you can take a look at our model performance in the chat box, and also fill out the feedback form so that we can improve and see what you guys want to see in the future. And yeah, I think that's all from us today. Thank you very much for attending, and really appreciate your time and effort. And yeah, we wish you all the best in your ML career. So if you have any question, you can ask us. Technical, non-technical advice, career planning, as long as ML related, you're welcome to ask.